Hello and welcome to this video. I'm Luca Barsellotti from the University of Modena at Reggio Emilia, and I'm going to present our work entitled Training-Free Open Vocabulary Segmentation with Offline Diffusion-Augmented Prototype Generation, which has been accepted at CVPR 2024. And before starting, I want to thank my co-authors Roberto, Marcella, Lorenzo, and Rita for their invaluable contribution. In this work, we are tackling the unsupervised open vocabulary semantic segmentation task, in which the model is asked to segment a given image according to an arbitrary set of categories described by text. It is unsupervised in the sense that the models should not be trained on dense annotations, like bounding boxes or segmentation masks, which are expensive to manually annotate and cannot cover an open vocabulary set of concepts. In this example, the inputs are the image on the left, depicting these three boats, and the set of categories on top, boat, water, sky, and buildings. The open vocabulary model receives these categories as text and predicts the segmentation masks on the right. The colors of the masks correspond to the color of the predicted categories. To tackle this task, the previous approaches rely on inducing a pixel-level alignment in a multimodal space between textual and dense visual features. The alignment is usually learned by performing an extensive contrastive training over a large set of image caption pairs. Methods like TCL and group fit exploit grounding mechanisms to force the segmentation capabilities to emerge. The main limitation of these approaches is that they lack a direct source of supervision about the localization of the concepts mentioned in the captions. Before presenting our solution, it is important to focus on three preliminary observations. First, text-conditioned diffusion models like Stable Diffusion can generate synthetic images for an open vocabulary set of concepts. Second, we can localize objects corresponding to words in the generated images through cross-attention. For instance, if we generate an image from a cat on the table caption, we can localize the cat and the table using cross-attention. And finally, self-supervised visual backbones like Dino and Dino-V2 exhibit strong semantic correspondence properties among local features. Hence, we propose to create an offline synthetic collection of embedding pairs composed of a textual embedding and a localized visual concept embedding. At inference time, the text embeddings are retrieved and their corresponding visual embeddings are used to segment the input image using local semantic correspondence. So we present FRIDA, that stands for Training-Free Segmentation with Diffusion-Augmented Prototypes. Our approach is composed of two main phases, a diffusion-augmented prototype generation phase and a semantic correspondence-based inference phase. So the first phase is carried out in an offline preprocessing step in which we generate a large set of images from captions using a diffusion model. In the meantime, we exploit the cross-attention to create the collection of embedding pairs composed of a textual embedding and a localized visual concept embedding from these generated images. The second phase is employed at test time to perform prediction over a given input image. First, we detect class-agnostic regions through superpixels. Then we use the input categories to retrieve textual and visual embedding pairs, and for each category we build a unique visual prototype embedding. Finally, we exploit the semantic correspondence of the self-supervised backbone to assign categories to regions. In this slide, I'm going to give a closer look at the offline phase. So first, we generate an image according to a conditioning caption, in this case, a person and a boat under a tree at a lake. Second, for each noun in the caption, person, boat, tree, lake, we use the cross-attention to extract its attribution map on the generated image. Third, we threshold the attribution maps to convert them into binary masks, one for each noun. Fourth, we extract local dense features using the visual self-supervised encoder DynoV2. And fifth, we perform region pooling between the local features and the binary masks to obtain a visual prototype for each noun. Finally, we use a text encoder to get a retrieval text embedding for each noun. In particular, we compute the weighted average between the embedding of a photo of noun, for instance a photo of a lake, and their time caption. In this slide, we are going to see the semantic correspondence-based inference. The inputs to the model are the image of the woman on the left and a set of n categories on the right. So first, let's see the global and local visual features extraction, that is the blue step on the left. First, we obtain class-agnostic regions using a superpixel algorithm. Then we extract local patch level features from the self-supervised visual encoder DynoV2. Having the regions and the patch level features allows us to perform a region pooling to build the region level features. And in parallel, we extract global features from the image using a multimodal image encoder like CLIP. So now let's move to the text-guided prototypes retrieval step, that is the red one on the right. So first, we extract the input category features from the text encoder, like the one of CLIP. We use these category features to retrieve the most similar text embeddings from the offline collection built before. And each of these text embeddings corresponds to a visual embedding. Hence, we average the visual embeddings assigned to each category to build its unique representative prototype. And finally, we compute both local and global similarities and ensemble them to obtain the final prediction. In this slide, you can see a comparison with other models from the current literature. Our proposed method Frida achieves state-of-the-art unsupervised open vocabulary segmentation performance over 5 datasets, which are commonly used as benchmarks in segmentation. And it is important to note that Frida does not require additional trainable parameters. Here we propose a qualitative comparison to demonstrate the quality of the segmentation results achieved by Frida. In particular, this slide shows the original input image, the ground truth, the prediction from TCL, and the predictions of Frida in 3 scenarios, without global similarities and superpixels, without superpixels, and considering all the proposed components. These results show that global similarity is necessary to reduce category noise, while superpixel produce masks that better fit the elements in the image. Frida exhibits explainability properties by analyzing what is retrieved and contained in the offline collection of textual and visual embedding pairs. Here we show some retrieved pairs when the input categories at test time are aeroplane and cat. Let's look closer at the first example for aeroplane. The text embedding is built by combining airplane with the entire caption, large white ship dock next to an airplane on the water. This caption is provided to Stable Diffusion to generate an image, and the cross attention is used to localize the noun airplane as an attribution map on this generated image. Then, by thresholding the attribution map, we obtain the mask on the airplane. To create the visual embedding of airplane on this image, we perform region pooling between this mask and the DynoV2 features. In this slide, we show that Frida can also handle in-the-wild categories represented as free-form textual inputs and is not restricted to a finite set of categories. This is possible because we build the retrieval text embeddings by combining the nouns with the caption in which they are found. For example, Frida can segment concepts as red double-decker bus, black white cat, and kitchen appliance. Here you can find the list of references that I cited during this presentation. For more details, refer to the official paper that is linked in the description of this video, along with the project page link. We will present our paper in the first session of Wednesday morning, so do not miss the opportunity to come and talk to us. Thank you for your attention and hope to see you in Seattle.